Let's have a look at integration. As it stands at the moment, we can't integrate logs. Okay? And in fact, we won't integrate logs until we see an extension 2 technique, which will allow us to do that. So what we're going to look at is doing the reverse of yesterday. And when we differentiated a log, we got derivative on function. So therefore, logically, if we integrate a situation where we see we've got derivative on function, it must go back to a log. So integral of the derivative on the function. So if you can create the derivative of the denominator on top, then we know that's going to be the log of the denominator. So what to look out for? You got a question like this. I suppose the first temptation is to say, let's put it in index form, because that's the sort of thing we do. But the power would end up being to the -1. And when you add 1 to the power over the power, you're going to get 0 on 0, and that's a problem. And so that's a little indicator. Hang on, something else is happening here. So this is probably a log situation. Can I create the derivative on top? At the moment it's 1, but that's all right. The derivative is a constant as well, because the derivative of the bottom's -3. So I can create -3 on top. Just got to multiply by -1/3 out the front to balance it. So we've got derivative on function, so that'll become log of 7 minus 3x, plus, of course, the constant. So same sort of thing here. Again, if we were to put that in index form, we get power of -1, no good. So can I create 8 on the top? Yes. 1/8 of 8. So we get an 1/8 of log 8x plus 5. What you're really looking for with polynomials is the order of the numerator is 1 less than the denominator. So on the bottom, the highest power is 6. So when you differentiate something to the power of 6, you get something to the power of 5. So I'd like 6x to the power of 5 on top. So balance it out, 1 6 out the front. So I know, all right, that'll be a 6, the log of the denominator, x to the 6 minus 2. 1 on 5x. Now this is an interesting question, depending on how you approach it. I could say, well, the derivative of the bottom's 5. So I'll have a fifth out the front. So we end up with 1/5 log 5x plus a constant. But if I do it a different way, because remember, we can always factorise constants out. So if I factorise out 1/5 and say, well, the integral of 1 on x, and if I integrate 1 on x, I get log x. Different answers. But they are actually the same. Why? That's it. I mean, I've written plus c for both. The reality is those constants would be different. Because if you use your log laws on the first one, you could break that up to be a 5th log 5 plus a 5th log x. And a 5th log 5 is just a constant. And so it's actually in the constant of the other one. Yeah. Both would be accepted. Okay, 4x plus 1 on 2x plus 1. Now, in order to do this, I've got to do a polynomial division. Oh, this is a nice easy one because they're linear functions. So if ever you see the order of the numerator bigger than or equal to the denominator, do a polynomial division. So, well, there's my little polynomial division. That means I can rewrite that as 2, and the remainder was -1. So -1 on 2x plus 1. I've now got 2 terms that I can go and integrate. Because 2, of course, will just become 2x. And I can create derivative on function for the other one. So you see the order of the numerator, the same or more. Do a polynomial division first. And then you should get something you can handle. So this one becomes 2x minus a half log 2x plus 1. Let's do a definite one. Nicely, the derivative is already there for us, so we don't have to do anything. Derivative of x squared is, of course, 2x. So subbing in. Now, technically, it's the log of the absolute value. Right? So I've just written x squared plus 1. In this case, it didn't actually matter, because x squared plus 1 is always going to be positive anyway. Because remember, you can't find the log of a negative number. So it's actually the log of the absolute value of whatever you get. Sub in 2, sub in 1, log 5 minus log 2, but using our log laws, we can turn that into the log of 5 on 2. Now, the reason why, if you look at your basic hyperbola over there, of course, its equation is 1 on x, so when you integrate it, you get log x. But if I wanted to find the area on the left-hand side of the y-axis, I would be subbing negative numbers in. And so I'd sub in the log of negative 2, for instance, minus the log of negative 1. But how do you find the log of the negatives? So that's why it's absolute value. The reality is it probably doesn't matter, because if you're doing a definite integral, you'd use your log laws to combine them together, and you'd end up with negative 2 divided by negative 1 becomes a positive. So it usually sorts itself out anyway. But you will notice in some answers they'll put absolute value there, and that's the reason why. Here's one of these ones where we differentiate first and then hence go and integrate. So there's a really strong chance my answer when I go and differentiate this is going to involve x squared log x somehow. Okay, got to use a product rule. Write down the first, diff the second, plus write down the second, diff the first. I end up with x squared plus 3x squared log x. So what I now know is when I differentiate x cubed log x, I will get x squared plus 3x squared log x. Therefore, logically, when I integrate the right-hand side, I will get x cubed log x, if I'll go back the other way. And so that's the idea I'm going to start with. I'm going to break it up into two different integrals, because the actual one I'm looking for is x squared log x. But it is just like an equation. I can move terms. So when I broke it up into the integral of x squared dx, I've moved that over to the right-hand side. And so now I have 3 lots of the integral x squared log x is equal to x cubed log x minus the integral of x squared dx. So let's integrate that. And that, of course, becomes a third x cubed. Divide everything by 3, and I've got my answer. So just because this was all one integral doesn't stop me from moving terms. Remember, we had that rule with integration. You can break it up and integrate each term individually and treat them like separate things, and you can move them. It is an equation at the end of the day. You can move things from one side to the other. Okay, 12D, 12E, ooh, a few asterisk ones there, 23.